Let me show you how to apply the method of reduction of order to solve a second order differential equation of the form a sub 2x, the second derivative of y, plus a sub 1x, y prime plus a sub 0x, y equal to 0. We have a homogeneous differential equation. Suppose you have one of the solutions that is denoted by y sub 1. Well, to seek the second solution, y sub 2, remember that y sub 1 and y sub 2 needs to be linearly independent. When we are saying that they are linearly independent, it means that if you form their quotient, it is non-constant. It must be a function. So if you do the division between y2 and y1, it is equal to a function like u of x. Then our goal is to figure out what is u of x. Y sub 2 can be written as u times y sub 1. Then you can take the derivative, substitute this back into the first and original differential equation that you have. Then you can apply the methods that you learned in calculus and find ux. Let's take a look at one example. Here we have a second order differential equation, the second derivative of y minus y equal to 0. One solution is given to you. E to power x is the given solution here. You want to apply the method of reduction of order to find the second solution, or y sub 2. But remember that since y1 is equal to e to the x, y2 is ux times e to the x. Let us apply product rule to find the first derivative and second derivative of y sub 2. The first derivative of y sub 2 is equal to the derivative of u times e to the x, so it is u prime e to the x, plus u times the derivative of e to the x, which is e to the x. Now use this first derivative to find the second derivative. The second derivative of y sub 2 is the derivative of u prime, which is the second derivative of u times e to the x, plus u prime times the derivative of e to the x, which is e to the x. At the same time, if you have a product rule here, you have u prime times e to the x. So you end up with 2u prime e to the x. And finally, u times the derivative of e to the x, which is e to the x. Now, substitute everything into the differential equation that you have. The second derivative of y minus y, in this case, we are working with y sub 2, is equal to, so this guy needs to be specified as y sub 2. It is equal to, we're just taking the derivative that we found here and substituting there over there. So you have the second derivative of u e to the x plus 2u prime e to the x plus u e to the x minus y sub 2, which is ux e to the x. But you have opposite terms. Get rid of them. Simplify as much as you can. This guy is simplified to the second derivative of u e to the x plus 2u prime e to the x. And you can set it equal to 0. Why? Because you have a homogeneous differential equation. It is equal to 0. Now, in setting this differential equation equal to 0, you only need to set the second derivative of u plus 2u prime equal to 0. Why is that? If I factor out e to the x and set e to the x equal to 0, this equation has no solution. Why is that? We are going back to algebra. From algebra, remember the graph of e to the x. It never touches x-axis. Setting e to the x equal to 0 has no solution. So we're not going to waste our time. Instead of setting e to the x equal to 0, we factor out e to the x and we set the second derivative of u plus 2u prime equal to 0. Now you have a second order differential equation that you can rewrite using substitution. We're going to introduce a new variable like w and set it equals to u prime. So if we do that, we can rewrite the differential equation as w prime plus 2w equal to 0. W is equal to u prime. So it is going to be substituted over there. But at the same time, if I take the derivative of w, it is equal to the second derivative of u So it becomes the second derivative of u. That's how you end up with w prime instead of the second derivative of u. What happened here? You have a first order linear differential equation that you already know how to solve. You can find the integrating factor. The integrating factor is e to integral px dx. But px is equal to just 2. So you have e to integral 2 dx. And then if you take the integral of 2 dx, it is 2x. So the integrating factor is e to power 2x. Now that you found the integrating factor, as you remember, you can multiply the differential equation by integrating factor left-hand side and right-hand side, and then start taking the integral of both sides. But remember that when we are writing it this way, e to 2x w prime plus 2w equal to 0, we can rewrite it as the derivative with respect to x of e to 2x w. Here we go. If you take the integral of both sides, you have the integral of dx, e to 2x w dx, and on the right-hand side, you have the integral of 0. So basically, you have e to 2x w equals to the integral of 0 dx is c sub 1. You can call it c or anything else. It helps us to rewrite w. W becomes c1 e to power negative 2x. Now, remember that we did this substitution. U prime is equal to W. So wherever you see W, you're going to substitute that by U prime. U prime is equal to C1 e to power negative 2x. So if you take the integral of both sides, you have the integral of U prime dx equals the integral of C1 e to power negative 2x dx. But what's the meaning of that? The integral of U prime is nothing but U. So instead of the integral of u prime, you just write u. But the integral on the right-hand side, you have c1 e to power negative 2x. We're going back to calculus. The integral of e to ax dx is 1 over a e to ax plus constant of integration. So u becomes c1 divided by negative 2 e to power negative 2x plus a new constant, which is c sub 2. What happens here? You can rewrite everything using this new function that you found. u2, which is ux e to the x, can be written as, you can just distribute e to the x here, and you get c1 divided by negative 2, e to power negative 2x times e to the x becomes e to power negative x plus c2 e to the x. So you can choose c2 to be 0 and c1 to be negative 2, and y sub 2 becomes e to power negative x. So the differential equation has two solutions. One of them is, let's go back to the original question and show you. This differential equation has two solutions. One of them is e to the x, and we found e to minus x using the method of reduction of order. So the fundamental set for this second order differential equation has two functions, e to the x and e to power negative x, by using the method of reduction of order. Now let me show you how to apply a shortcut. In applying shortcut, if you have a non-homogeneous differential equation, a sub 2x, the second derivative of y, plus a1x y prime plus a sub 0x y equal to g of x, and if you have y1 as the solution of this differential equation, you can find y2 applying the following formula. y2 is y1 times the integral of e2 negative integral pt dt divided by y1 to the second power. So let's go over one example now that we are here. Consider the following second order differential equation. You have x2, second derivative of y, minus 3xy prime plus 4y equal to 0. You already have one of the solutions. So in the method of reduction of order, you either guess the very first solution or it is given to you. Form the standard form of the equation. Here we have the second derivative of y minus, you have 3xy prime divided by x squared plus 4y divided by x squared equal to 0. Now, y2 is equal to x2, which is given to us, times the integral e2 3 integral dx over x. So negative 3 divided by x is going to land on the power of exponential function. So here when it says negative integral pt dt, this guy is going inside the integral. And since you have a negative sign already in front of the integral, the negative and negative disappear. And on the denominator, you have x squared to the second power, which is x to the fourth. Well, we're going to go back to calculus and solve this integral. You have x squared integral of e2 3 integral dx over x. But remember that e2 3 times integral dx over x going to be, this guy is ln of x. So since you have ln of x, we can take this 3 and move it as the exponent. So this guy becomes e to ln of x to the third. Exponential function and ln function, they are inverse of each other. So it disappears, identity function. So you end up with x to the third. Now what? This guy is equal to x squared, the integral of x to the third divided by x to the fourth. Remember that this is equal to x to the third. So x to the third divided by x to the fourth happens to be dx over x. But again, this is equal to x squared times ln of x. So we easily found y sub 2. So now you can write the general solution as c1, y1, which is x squared, and c2, y2, which is x squared ln of x. So on the exam, in the homework, you can either use the direct substitution or you can use this nice shortcut. But remember that if you want to apply this shortcut, please make sure to write everything in standard form first.